Relativity continues. What about the addition of velocities? We know that Galilean relative velocities cannot be applied to objects moving near the speed of light, which can't just simply add velocities together indefinitely, because there is a speed limit in the universe, and that is the speed of light. So, what do? What happens if we are adding velocities that are really high, close to the speed of light? What do we come up with as the combination of those velocities? Well, the Lorentz velocity transformation equations are derived using special relativity considerations, and they allow us to add velocities on a relativistic scale. If we are going from a rest frame S to a moving frame S prime, then the velocity viewed in the moving frame, or the velocity of an event in the moving frame, u sub x prime, is equal to the velocity of that event witnessed in the rest frame minus the relative velocity between frames over 1 minus the velocity of the event, relative velocity divided by the speed of light squared. So this allows us a transformation from an event in a rest frame to a moving frame. So for a particular event, u sub x prime is the event in the moving frame, S prime frame. U sub x is the velocity seen of the event in the rest frame. V is the relative velocity between these two frames. So we're going from a rest frame S to a moving frame S prime. Say you want to go the other way around. You want to go from a moving frame S prime to a rest frame S. To do that, you would take the same formula, replace the relative velocity v by a negative v in the equation, and interchange the roles of u sub x and u sub x prime. So, going from a moving frame to a rest frame, we have that the event of the velocity in the rest frame is equal to the event as measured in the moving frame plus the relative velocity between frames, 1 plus the event in the moving frame plus times velocity in the relative velocity divided by c squared. So we just replace v by negative v, interchange the roles of the events from moving frame to rest frame. So u sub x is the velocity in the rest frame S, u sub x prime is the velocity in the moving frame S prime, and v is the relative velocity between those two frames. Let's try this out. Here's a problem. Two spacecraft, A and B, are moving in opposite directions. An observer on Earth measures the speed of spacecraft A to be 0.75 c and the speed of spacecraft B to be 0.85 c, and they're headed towards each other. Find the velocity of spacecraft B as observed by spacecraft A. If this were a Galilean problem, then you would conclude that it's 0.75 c plus 0.85 c would be 1.6 c and be above the speed of light, and that can't possibly happen. So we're going to use these new transformation equations for velocity addition to solve this problem. So first thing, let's identify our variables and our frames. One observer's on the Earth, the other and at rest. The other one is in spacecraft A. So A is going to be our moving frame. The Earth is going to be our rest frame. The relative velocity between the two will be the velocity of spacecraft A, because that's the moving frame velocity. So our relative velocity v will indeed be the velocity of that moving frame A, 0.75 c. So we have one spacecraft, it looks like a Romulan spacecraft, moving at 0.75 c. Spacecraft B is the event, and in the Earth rest frame, it's moving in the opposite direction towards spacecraft A. So its velocity will be negative as it's going in the opposite direction, and its speed is 0.85 c. So as far as the Earth frame is concerned, its velocity is a negative 0.85 c, and that's the event that we wish to transform to the perspective of A, the moving frame. So we wish to find this event, use of x prime, using our transformation equation. Relative velocity is 0.75 c. The event in the rest frame of Earth is a negative 0.85 c. Our transformation equation is the event velocity minus the relative velocity over 1 minus the event velocity, relative velocity over c squared. So we have the event, negative 0.85 c, minus the relative velocity, 0.75 c, 1 minus the event, negative 0.85 c, times 0.75 c over c squared. The c squares cancel out. In the numerator, I'm going to have a negative 1.6 c, and in the denominator, I'm going to have 1 plus 1.6, or let's see, 1 plus 0.85 times 0.75, which is 0.63. So this is going to give us a negative 0.977 c. Still less than the speed of light, but this is how fast it looks to the Romulan spacecraft to have this Klingon spacecraft coming towards them closer to the speed of light, because they're both moving pretty fast towards each other. It's negative because it's coming in towards them. So that's how you would use this velocity addition formula for relativistic speeds. Here's a quote from Einstein, 1952. What led me more or less directly to the special theory of relativity was the conviction that the electromotive force acting on a body in motion in a magnetic field was nothing else but an electric force. So what he was thinking was electromagnetism, which has electric fields and magnetic fields, was really nothing more than just truly electric fields. If you found the right transformation to the right frame of reference, you could transform out the effects, the residual effects of moving charges, which is the magnetic field, and just create it all to look like one electric field. Brilliant. This is the beauty of Einstein's genius, is that he could look at difficult things and make them simpler. And the understanding is simpler, makes our understanding easier to look at other things in the universe. So here's how it looks. You have some charges. These charges have electric fields, and if those charges are moving, we generally think of currents, and we call that magnetic fields associated with moving currents. But what he's saying is that's just a residual or circumstantial effect of the fact that these charges are moving. If I can transform these charges to a moving frame, they will be at rest in that moving frame, and hence I only have to deal with an electric field. I don't have to calculate a magnetic field. That one electric field deals with the whole situation. Utter brilliance. So Einstein was pretty brilliant, but maybe other people thought of this earlier, because if you look at hieroglyphics and pictures, you might find E equals mc squared on the cave wall. Here's another quote from Einstein. The most important result of a general character to which the special theory of relativity has led is concerned with the conception of mass. Before the advent of relativity, physics recognized two conservation laws of fundamental importance, namely the law of conservation of energy and the law of conservation of mass. These two fundamental laws appear to be quite independent of each other. By means of the theory of relativity, they have been united into one law. In other words, he's saying mass is the same as energy. Energy is the same as mass. Again, Einstein is making the universe simpler for us. What's more simpler than making it more compact easier to understand. Mass and energy are the same thing. Wow. Here's a Gedanken, a thought experiment. That's what Einstein called his thought experiments to help visualize things, a Gedanken. Einstein's box. We have a box, and enclosed in that is a photon isolated system. There's going to be a burst of photons of energy from one end of the box, and it's going to travel towards the other end of the box, a distance of L for the length of the box. The box itself has a mass m. This radiation carries a momentum equal to its energy divided by the speed of light. Since momentum is conserved, the box should recoil with a speed v given by the momentum of the photon divided by the mass of the box. In other words, the momentum of the box, mv, will go in the opposite direction. So the velocity of the box will be forward by a negative 1 over m, energy of the photon burst, divided by its speed of light. After traveling for a time delta t equal to the length of the box divided by c, that's the time it will take for the photons to reach the other end of the box. The radiation will collide with the other end of the box, giving it an impulse. Since the box was moving with impulse that started it, the same magnitude, it will now come to rest. So the box will come to rest after being hit by this photon pulse. The result of this process, finally, is to move the box some distance, delta x, equal to the velocity of the box times this change in time. Velocity equal to negative e over mc, and the change in time was L over c. So this is going to be equal to negative e times L over the mass of the box times the speed of light squared. But this being an isolated system, we can't really believe that the box's center of mass has moved just out of the blue. We can postulate that the radiation has carried with it an equivalent mass such that the center of mass of this isolated system remains the same. So we're going to say that some equivalent mass for this photon burst times the distance it traveled, which is L, should equal the mass of the box times plus the distance it's traveled, delta x. One of these will be positive, one will be negative. So when we add them together, we'll still maintain a center of mass at position 0. Putting these last two equations together and substituting in for the delta x that we have the equivalent mass of this photon burst times L plus m times negative e times L over m times c squared equals 0. Masses of the box cancel out, and so do the L's if we divide both sides of the equals by L. And we get this. The mass of the photon burst is equal to the energy of the photon burst divided by the speed of light squaring. Or the energy of the photon burst is equal to mc squared. How about that? This is the first instance of associating radiant energy with an idea of an equivalent mass. Well, maybe dinosaurs thought about this. They were on the Earth for 180 million years. They had a lot of time to think about it. But after all that time, they came up with E equals mc to the 10th, not mc squared. It's probably why they became extinct. Rest energy. A particle has energy by virtue of its mass alone. A stationary particle with zero speed and hence zero kinetic energy still has energy. It has an energy proportional to its inertial mass. Its rest energy, we call it E sub naught, rest energy, is equal to its mass, rest mass, times c squared, speed of light squared. The massive particle may be completely convertible to energy, and pure energy may be converted to particles by this equation. It really is the equivalence of energy and mass. I know we have that c squared multiplied in there, but c is just a constant. And if we use the right coordinate system or right unit system, then we basically are saying energy equals mass. How beautiful is that? To account for conservation of momentum in all inertial frames, the definition of momentum must be modified. Our relativistic momentum is now gamma times mass times velocity, not just mv, but gamma times mv. For most everyday situations, gamma is going to be 1, momentum is mass times velocity. But in relativistic terms, we have that momentum is gamma times mass times velocity. V is the speed of the particle, m is the rest mass, gamma is defined as before 1 over the square root of 1 minus relative velocity squared over c squared, or the velocity of the particle squared. When a mass is moving, it has a total energy associated with that kinetic energy plus rest mass. Depends on its speed. The total energy of a moving particle is gamma mass c squared. So the energy of motion, just the kinetic energy portion of a particle, will be this total energy minus its rest mass. So that will be equal to E minus E naught, or gamma minus 1 times mc squared. That will be the kinetic energy of a moving particle. If we take the values of energy and momentum, square them and subtract them, multiplying the momentum by c squared, we have E squared minus momentum squared c squared. What do we get? Just for grins. We have gamma squared, mc squared for our total energy squared, momentum gamma mv squared times c squared. Factor out a gamma on both terms, and we have mc squared squared minus mc squared squared v squared over c squared, which we can factor out a mc squared squared, and we have gamma squared, which is 1 over 1 minus v squared over c squared, times 1 minus v squared over c squared. Those cancel out, and we end up with mc squared squared. Sound like a rap artist. And we have E squared minus momentum squared c squared equals mc squared squared. And so we have our total energy squared is equal to the momentum squared times the speed of light squared plus the rest mass squared. For particles that have 0 rest mass, where m is 0, like photons, then we would set m equal to 0, and we'd simply have E squared equals p squared c squared, or the energy is equal to the momentum times the speed of light. That's for photons. This relates to total energy and linear momentum of photons which travel at the speed of light and have no rest mass. They have equivalent mass due to their energy, but not a rest mass. It's convenient to express the energy of subatomic particles in units of electron volts. You may recall 1 electron volt is 1.6 times 10 to the minus 19 joules. So the rest energy of an electron is the mass of an electron times the speed of light squared. 9.11 times 10 to the minus 31 kilograms, 3 times 10 to the 8 meters per second, square that, is 8.19 times 10 to the minus 14 joules. That is the rest energy of an electron. And if I convert that to electron volts, that is 0.511 mega electron volts, or about half a mega electron volt. The rest energy of a Proton is the mass of a proton times the speed of light squared. 1.67 times 10 minus 27 kilograms times 3 times 10 to the 8 meters per second squared. 1.5 times 10 minus 10 joules. Convert that, 938 mega electron volts. We can see that the rest energy of a proton is almost 2,000 times the rest energy of an electron, going by the mass ratio. Pair production. An electron and a positron are produced, and the photon will disappear. So the energy, pure energy of a photon, can be used to create an electron-positron pair. Positron is the antiparticle of the electron. It's antimatter, since it has the same mass but opposite charge. This must be done in the vicinity of some other atom or molecule, so that everything needed can be conserved. In other words, momentum energy must be conserved. The photon energy must go into the mass and energy of the electron-positron pair, but momentum must be conserved as well. So we must have some kind of other atom nearby to help absorb the recoil. Charge must also be conserved, so that's why you have an electron negative and a positron positive, so the total charge is still neutral. Minimum energy required would be the rest mass of the electron and the positron, which is 0.5 mega electron volts, and then the two of them together would be about 1 mega electron volt required. You also could have pair annihilation. Take matter and antimatter, bring them together. They can annihilate each other and give you energy. In pair annihilation, an electron-positron pair produces 2 photons, the inverse of pair production. You can't get 1 photon because you have to still conserve momentum. You can't produce a photon and have it just travel in one direction with momentum. You must have 2 so that your total momentum remains constant or 0 if these 2 were annihilated at one point. So, momentum must be conserved. We'll have 2 photons produced in pair annihilation. Marshmallows. If a marshmallow were traveling at 99.99% the speed of light and it hit the Earth, what would happen? Well, here's the Earth. Here's a marshmallow traveling at 99.99% the speed of light. At that speed, what is our gamma? 1 over the square root of 1 minus v squared over c squared. So that's going to be 1 over the square root of 1 minus 0.9999 squared. Gives us a gamma of 70.7. So the marshmallow's energy will be equal to gamma times the rest mass. The marshmallow's mass is 10 grams. So we have gamma times 0.01 kilograms for 10 grams. Speed of light squared, 3 times 10 to the 8 squared. Gives us a total energy of 6.4 times 10 to the 16 joules. This would be larger than the largest hydrogen bomb we have at the moment. That much energy by a marshmallow traveling at 99.99% speed of light hitting the Earth would produce quite an explosion, and it'd be quite a catastrophe. So it's probably a good thing we don't have marshmallows traveling at us at 99.99% the speed of light. But we do have other particles, gamma rays and particles from the universe headed our way, traveling at very close to the speed of light, and those particles could cause us problems from time to time because they actually have quite a lot of energy, something to worry about at various times. All right, let us go on and look at general relativity.